Hello everyone, welcome back to lesson number 30 where we're talking about volume, and we've been talking about volumes using cross sections. In the first video we talked about a square and we talked about an equilateral triangle. In this video I'm going to talk about the isosceles right triangle and the semicircle, and then I'm going to summarize and give you a really straightforward, simplistic way of doing these problems where you don't have to do all the crazy methods that I'm doing right here necessarily. I'm going to start with example number 4, because this one's actually more of a BC thing with the isosceles right triangle, and I'll clarify that when we get to it. So let's go ahead and continue on with example number 4, where it says the base of a solid is the region bounded by y equals 1 minus x squared and y equals x squared minus 1. The cross section of the solids are perpendicular to the x-axis, and again, they're going to always be perpendicular. They're semicircles, so find the volume. So the first thing we want to do is we want to just kind of get a general sketch of what these graphs look like. And so, when you're doing this, the easiest way for me to just tell you guys about these problems is the fact that, well, when x is equal to the positive and negative 1, this graph right here is going to be on the, so actually let's do this. Let's do positive and negative 1 here, and this graph will also have a y-intercept at 1. So I know this graph is, and it's also a negative x squared, so I know the graph is going to look something to the behavior of this. We always just want a little rough sketch, and honestly, guys, sometimes these are mostly calculator questions anyways, so it's just really easy for us to kind of graph that. The second graph that you guys see here, well, this is going to be an x to the 4th graph. Again, positive and negative 1 will make this actually end up being 0. And then I know that my y-intercept's at negative 1, and it's positive, therefore leading coefficient is positive, so I know it's going to open up like this. So this just gives me a good little generalization of what's going on with the problem. I know immediately that when I integrate this volume, that I'm going to integrate it from negative 1 to 1. And so that's actually pretty easy for us to look at. And so what we want is we want to sketch semicircles. So again, we're going to use an area kind of thing with this, but this is going to be our little thing. And this is going to be our little semicircles that we're going to be sketching. And so if I go ahead and draw myself a semicircle, the x is going to be this distance right here. Now, again, what I was trying to explain in the first video is that you guys already know how to find this distance. So let me go ahead and do this in the hot little pink. So these distances, well, based on area, you know that this x, let's call this distance x, this x is going to be represented by my top function minus my bottom function, because everywhere over here, this is always the top and this is always the bottom. So this x, this height, this difference is going to be the green curve, which you guys know as 1 minus x squared, minus my bottom curve, which is going to be x squared, or x to the 4th minus 1. So I know that's going to be the x. So once I find the area of a semicircle using simplistically x, because I don't want to put this craziness in there, then I can substitute in x when I find it. Remember, the volume is going to be equal to the integration of the area of the shape that we're trying to find. So if I ask you guys to find the area of a semicircle, well, that's simply going to be 1/2. Well, it's actually going to be pi r squared divided by 2, right? It's a semicircle. Well, the radius of this circle is simply going to be x divided by 2, right? If this whole thing is x, we cut this down the middle, it's going to be x over 2. So that's going to be what our radius is equal to. So then I can go ahead and clarify this as saying pi over 2, and then I can say this is going to be x over 2 squared. All right, and then I can simplify this down a little bit more, and I'm going to get pi x squared on the top, and then I've got 2 times 2 squared, which is going to give me 8. All right, so I got pi over 8 times x squared. So then if I actually ask you guys to find the volume of this thing, again, third example we're doing here, we're going to plug this right here into our problem. Again, the thickness of our semicircle would be our dx, so we always have our dx here. And we're going to integrate this from negative 1 to 1. And that's simply all we're going to do our setup. Now, me to actually solve the problem, what I want to do really fast is I'm going to pull out the pi over 8. I'm going to go ahead and do negative 1 to 1. And then I'm going to go ahead and plug in now what my x is. So it's going to be 1 minus x squared minus x to the 4th minus 1. And I'm going to put a big old bracket around this. and I'm going to square it dx. And then using my graphing calculator, I'm going to go ahead and say, okay, this is 1.9348, all right, or 1.935 if you want to think about it like that. So what I wanted you guys to notice really quickly in this example is that, again, my function is squared, and then I've got some random number on the outside. So I'm going to just really quickly take us a flashback to the last video. But again, remember, when I found my area, it ended up being some number times an x squared. So think about that. So let's go back, flashback for a second. So the very first example I did was a square, and notice that the area that I found was x squared, and the number ends up being 1 because there's just no number in front of it, right? And then let's look at what happens when I found the area of an equilateral triangle. Look at this. It's not shocking that our functions simplify down to x squared, and then we had some random number. So in all these cross sections, your area will always be some number times x squared. So let's do the last example. Okay, so this example is a little bit more challenging because this says hypotenuse on the base, and usually it's going to be a leg, but let's just go ahead and just look at this problem. So it says this base of a solid is the region inside of the circle, which is a radius of 2. So we can go ahead and draw ourselves a circle of a radius of 2. So we can do that if we want to. And it says from the volume of the solid, if every cross section perpendicular to the x-axis is an isosceles right triangle. So an isosceles right triangle. So remember, isosceles right triangle. Now, this is saying that the hypotenuse is on the base. So it's going to look something like this. Right? Something like this. So what would normally be an easy example is they would tell you guys that the leg was on the base. So we're going to kind of do both of them at the same time. So I'm going to talk about it if it said leg on the base, and then the BC one where we talk about the hypotenuse. So what I end up doing, guys, is I go ahead and create myself a isosceles right triangle. And if I make my base x, this is also going to be x, right? Because again, isosceles right triangle, this is going to be the same as this right here. And then if I use Pythagorean theorem, I'm going to get x squared plus x squared is equal to the hypotenuse squared. So this would end up being 2x squared equals the hypotenuse squared. And so this hypotenuse would just be the square root of 2 times x. And you guys already know that because you know your 45, 90 triangles from geometry. Or at least if you didn't, well, that's the easiest way to do this problem. So if I try to find the area of this triangle, it would be 1/2 base times height. So again, ladies and gentlemen, there's our number and there's our function. There's our function. And so in a AB class, our x would simply be what our function is. So you would solve for y. So actually, let's go ahead and solve for y in our function. So we get that y squared is going to be equal to 4 minus x squared, and that y is going to be equal to the positive and the negative square root of 4 minus x squared, where the positive is going to be this region right here, and the negative is going to be this region right here. Now, what we have to understand is that, again, for BC calculus, that this height here, and this goes back to optimization, if you will, this height here, if this distance is x, right, and I really, really wish I should have made this bigger, but if this distance here is x, then this height is simply going to be y equals the square root of 4 minus x squared, right? So this distance here is going to be the square root of 4 minus x squared, based on the fact, like I said, if we did like ourselves a little rectangle, this is x, this would be the y value. Well, our y value is going to be this. So this is also, this would technically be the negative, right? This is going to be the negative side, but again, because it's a distance, we're going to also call this 4 minus x squared. So this hypotenuse, the hypotenuse is actually going to be, the distance would be 2 of these. So our hypotenuse would be equal to 2 times the square root of 4 minus x squared. And the reason why you do that is you can think about it 2 different ways. Well, this distance, this is symmetric to the origin, to the y-axis, to the x-axis, right? It's a circle. So if this distance is square root of 4 minus x squared, this distance is also 4 minus x squared. The other way you guys can do this, and I'm going to get rid of this one quick second, but I just want to say, if again you are trying to find the the area between two curves, you would take the top curve and you would subtract the bottom curve. And so the top curve would be 4 minus x squared. Our bottom curve would be negative square root of 4 minus x squared. And if I took these and subtracted one from the other, it would be this minus the negative and be plus or positive, which would give you the 2. So that's just another way of thinking about how we can find this distance right here, right? The distance of our hypotenuse of our triangle. And again, I'm just really trying to tie in our lesson number 29 with the lesson that we're doing right now. So how does that actually help us? Like, how does it help us? So we now know that this whole hypotenuse is going to be 2 square root of 4 minus x squared. And so I can now find, and let me just call this A and A. So I know that I can find this side now based on the fact of Pythagorean theorem. So I can go back and say that A squared plus A squared is equal to 2 square root of 4 minus x squared, all quantity squared. And so I'll get 2a squared is equal to, and again, in this case here, if I can find a, then I know what the area of this triangle is going to be. It's going to be 1/2 a squared. So I'm going to get, this is 4 times 4 minus x squared. I can divide by 2, and I get 2 times 4 minus x squared, and then I can take the square root of both sides. Or actually, let's just leave it like this. I can just leave it a squared. Remember, because the area of this triangle is 1/2 a squared. So my area is going to be 8 minus 2x squared. So that's going to be our area of our triangle is 1/2 of this function right here. So this will be times 1/2. And now this is going to give us our area of our problem. So we want to integrate that. We want to integrate this. So let me get rid of a lot of this craziness. So our volume is going to be equal to the integration of, and so we're going to plug all this stuff in, 1/2, and then 8 minus 2x squared. Now, I want to tell you guys really quickly that the 1/2, as we had talked about previously, I told you guys that when we found the volume, it's 1/2 x squared. Well, okay, here's our 1/2, and we've already squared our function. We've already squared our function here. So this works like this, and then again, this is our dx, and then we're going to integrate this thing from our lowest bound to our highest bound. And so our lowest bound is going to be -2, and our highest bound is going to be 2. So our left bound and I should say left bound and right bound, not lower bound, but our left bound -2 to +2. So this is what we're looking at. And this is it. This is our answer to our problem, and we're going to get 10.667. 10.667. So let me summarize what I just did, because I know this was probably not my best. I know it's not my best video because these concepts can be just so difficult, and I probably should have done 4 videos of each lesson. But anyways, let me see if I can summarize it for you, and hopefully you guys can just understand what's going on here. So let's look at the summary. And this is the summary of the cross section. And I may tell my students in my class, just come to go to 13 minutes into the second video, and then you'll understand stuff. So this is going to be the summary for cross sections for volume. Cross sections for volume. So if we look at the square, actually, let's do it this way. So general thing for this, volume is going to be equal to the integration of some value k of AB of your function quantity squared. Now, this is going to be your height. So sometimes you may see, and so I'm going to actually write it like this too, because this is normally what you would see, f of x minus g of x quantity squared. And I will do a third video eventually with you guys so you can see what this is. So here's our equation. This is our general cross-section formula. And again, this is just the height of our curve. So if I give you guys, and let me actually differentiate these really fast. So if I were to give you guys this one, this would be something that would just probably be bounded by the x-axis and some function curve. So this, f of x, would simply be the curve of this minus 0. However, if I give you guys another picture where I give you something like this, and I want the cross-section of this whole thing right here, well, the f of x would be this, and the g of x would be this, right? Because again, going back to lesson number 29, this is how you found this area. Because remember, volume is just the integration of area. So these are your two functions. This is normally the one that you're going to see. This is the one that we use for cross sections, and the k is going to be dependent on the shape. So for square, the k is going to simply be 1. If I give you guys a isosceles right triangle, then your is going to be equal to 1/2. If I give you a equilateral right triangle, your k is going to be equal to the square root of 3/4. And then if I give you a semicircle, I forget the r, give me the I, oh my god, it's going to be pi/8. I told you guys at the very beginning of the first video that there was a fifth thing, a rectangle, and the rectangle, the dimensions usually should be given to you. So if I say a rectangle that's a 3x5, then your k would be 3/5. Or if it said 5/3, then it'd be 5/3. They would usually tell you by the order that's listed on the problem. So I hope this was somewhat helpful for you. We're going to do more examples later in life, but in the next video, we're going to talk about washers and desks. So I'll see you guys in the next video.